I want you to do something for me, just for a second. Look around the room you're in right now.
Yeah, take a look around.
Like, look at the chair you're sitting on, or, the walls holding up the ceiling, maybe the device you're actually using to listen to this.
It all looks pretty normal, right?
Right. Take a look at the window if you have one. Everything probably looks incredibly still,
Yeah.
perfectly peaceful, quiet. But what if I told you that every single object you're looking at, I mean, every beam, every pane of glass, every tiny fiber in your chair is actually locked in this invisible high-stakes wrestling match?
It's a brilliant way to visualize our physical world, honestly.
Mm.
Because, to the mind of an engineer, nothing is ever truly at rest.
Never.
What you're perceiving as this perfect stillness is actually a hyper-violent stalemate.
A stalemate of epic proportions, and that invisible tension is exactly what we're unpacking today. Welcome to our deep dive.
Glad to be here.
We have this incredibly fascinating stack of research sitting in front of us today. It's a collection of engineering principles and case studies from this presentation, brilliantly titled Forces in Engineering, the Invisible Architects.
And we should mention the presentation itself is laid out in this font called Space Grotesque.
Oh yeah, it gives it this super sleek, modern vibe right off the bat.
It really does.
So our mission for this deep dive is to basically unmask these invisible forces. We want to figure out the rule book they play by, how they govern literally every single physical interaction in the universe, and, most importantly, how human engineers actually manage to wrangle them to build in the modern world.
It's a huge topic.
It is. But before we get into the heavy math and the physics of it all, there's something in these notes that completely, it just caught me off
You're
guard.
talking about the philosophical framework.
Yes, because, you'd think a deep dive into engineering and physics would start with, I don't know, Isaac Newton, or a bunch of equations about load-bearing beams.
That's the standard textbook approach, yeah.
Right. But the material we're pulling from today, it actually grounds all of this math in deep ancient philosophy. It starts by introducing this idea of a universe existing in a state of perfect, intentional balance.
Which is beautiful.
It really is. And it frames the entire profession of engineering around these two Islamic concepts, amana and khalifa.
Those two concepts completely reframe what it actually means to build things. Let's break them down.
Let's do it.
So the word amana, it translates to a sacred trust. And in the context of our research today, it suggests that engineering is not, merely a job.
It's not just clocking in and out.
Exactly. It isn't just this technical profession where you plug numbers into a calculator and go home at 5 o'clock. It is a profound, almost spiritual responsibility to protect human life.
That raises the stakes immediately. It takes this from being a dry textbook topic to a literal life or death responsibility.
It absolutely does, because think about it, right? When a structural engineer calculates the load capacity of a steel beam for a new hospital, they aren't just solving a math problem on a whiteboard.
No, they're not.
They are holding the lives of thousands of patients, doctors, and nurses in their hands. If they miscalculate, people die.
Wow. Yeah.
So that weight, that immense burden of safety that is the amana, it is a trust placed upon the engineer by society.
And then the research pairs that sacred trust with the second concept, which is khalifa.
Right. And khalifa translates roughly to stewardship.
Stewardship.
Yeah. So this is the idea that human beings, and engineers in particular, are stewards of the earth. They aren't just haphazardly making things up or forcing nature to do what they want.
They're not the bosses of nature.
No, they are uncovering the natural order that already exists in the universe. And they are tasked with applying those principles ethically and sustainably. You're a caretaker of the physical laws.
And to really hammer that point home, our source material includes this incredibly beautiful quote from the Quran.
It's a great quote.
It is. It's from Surah Al-Mulk, chapter 67. It says, "You do not see in the creation of the Most Merciful any inconsistency. Then return your vision twice again. Your vision will return to you humbled while it is fatigued."
Yeah.
Now, I am obviously not a physicist, but that sounds an awful lot like a highly poetic description of the scientific method.
It is exactly that.
Yeah.
It is an ancient observation of universal consistency. You do not see any inconsistency. That right there is the fundamental bedrock of all science and engineering.
Because the rules don't change.
Exactly.
Yeah.
Gravity does not take the weekend off.
Yeah.
Friction does not randomly change its properties depending on its mood. The speed of light is a constant.
Right, right.
The universe is incredibly aggressively reliable.
Yeah.
You can test it. You can, as the quote says, Return your vision twice again, and the rules will remain the exact same.
And because the rules are consistent, we can actually design real solutions within them. Like, if gravity occasionally just pulled sideways on Tuesdays, we could never build a skyscraper.
They'd be living in caves.
Seriously. But I love the end of that quote, too. It says, your vision returns humbled and fatigued, which is frankly how I feel whenever I try to do, like, advanced calculus.
It's a very natural reaction, honestly, to contemplating the sheer scale of the universe. When you truly realize the forces at play, the immense, invisible pressures holding a star together, or, just the forces holding the molecular structure of your coffee cup together, it is deeply humbling.
Well, consider me properly humbled.
Good.
And I think that sets the perfect tone for you, the listener, as we go forward. We aren't just learning mechanical physics today. We are learning about the immense ethical responsibility of wielding the fundamental forces of nature. We're exploring how we maintain that sacred trust.
Absolutely.
So let's open the invisible rulebook. Because before an engineer can act as a good steward, they have to define exactly what it is they are dealing with. What actually is a force?
At its most basic, foundational level, a force is simply an interaction that changes the motion of an object when it's unbalanced. If you want the absolute simplest definition, it is just a push or a pull.
A push or a pull. See, that feels almost too simple for the amount of math involved in engineering.
It is simple in concept, sure, but it gets incredibly complex in application. Because forces don't just exist as these vague ideas floating around. They are what we call vector quantities.
Vector quantities.
Yes, and this is a completely non-negotiable rule in physics. A vector demands two very specific pieces of information. It needs magnitude, and it needs direction.
Okay, let me make sure I'm wrapping my head around this. Magnitude is the how much, right?
Right.
Like the sheer amount of power or effort. And direction is the where. So it's kind of like giving someone driving directions. If you call me and say, hey, I need you to drive 50 miles at top speed, that's the magnitude. You've given me the effort.
But you have no idea where you're going.
Exactly. It is completely useless information if you don't tell me which way to point the car. Am I driving north, south? Am I driving straight off a cliff into the ocean?
That is a perfect analogy. The direction is just as critical as the amount of effort. If an engineer is, say, designing a retaining wall to hold back a mudslide, they can calculate the exact weight of the mud, that's the magnitude.
The how much?
Right. But if they incorrectly calculate the angle, the direction that the mud will strike the wall is going to collapse. Vectors force us to account for both the power and the path of the push or pull.
Okay, so we have our definition. A force is a vector, a push or a pull with a specific strength and a specific aim. But as I read further into our research, I noticed this big split, what I'm calling the grand divide.
Ah, contact versus field.
Yes. The sources classify every single physical interaction into two massive categories: contact forces and field forces. Now, I'll be honest, the contact forces make total intuitive sense to me. The definition is totally literal. They require direct physical touch.
Yeah, contact forces are highly intuitive because we experience them physically with our own bodies every single minute of the day. Whenever objects physically touch each other, boom, you have a contact force.
Right.
Think about the structures you walk on, mechanical springs, the friction of your shoes on the floor.
The notes we gathered give some really great everyday examples to kind of ground this. They call it the macro and the micro. Like, for a contact force, think of pushing open a heavy, thick glass door at an office building.
Yeah, your hand physically touches the glass.
Exactly. You apply a pushing vector, the door opens. Or think of a soccer player kicking a ball. The cleat violently collides with the leather. The energy transfers through that direct physical contact.
And we also have resistance contact forces.
Oh, like braking.
Exactly.
Yeah.
Imagine a car slamming on its brakes. The rubber tires aggressively drag against the rough asphalt. The physical friction between the road and the tire is what arrests the motion. In all of those examples, the point of interaction is entirely visible. You can point your finger exactly at where the force is happening.
Right. I can see the foot hit the ball. I can literally smell the burning rubber on the road. But then we cross the divide into the second category: field forces.
This is where it gets weird.
Yeah. Because our notes define these as acting invisibly through a field of energy that extends across empty space. Now, I have to push back on this a little bit, because intuitively that just sounds like actual magic.
It does.
Like, how do you push something without touching it? And more importantly, how does an engineer build a massive bridge or a machine based on something they can't even see or touch?
It absolutely sounds like magic. Historically, before we had the map to explain it, people literally did think it was magic. But field forces are just as mathematically rigid and reliable as a physical push. A field force is an interaction where objects exert pushes or pulls on each other without any physical contact whatsoever.
Okay, what's a real-world example of that, like a big one?
Well, the most obvious one is gravity. Think of a satellite orbiting the Earth. It is hundreds of miles above the planet, floating in the total vacuum of space. There's no rope tying it to the ground. There's no physical structure holding it. Yet the immense mass of the Earth creates this gravitational field that reaches out across the empty void and constantly pulls that satellite inward, keeping it in a perfect circular orbit.
Okay, yeah, and the research also points to magnetism, like a magnetic security door in a highly restricted building. There's no mechanical latch. There's no metal deadbolt sliding into a frame.
Right.
It's just a heavy metal plate held flawlessly tight against the wall by a magnetic field.
Exactly. And the profound takeaway for the engineer here is this. The math does not care if the force is visible or invisible.
Interesting.
It doesn't care if you can touch it or not. Whether you're dealing with the physical friction of a car tire or the invisible magnetic attraction of a security lock, the fundamental equations of force, those vectors of magnitude and direction, they remain completely identical.
So the universe really is consistent, like the quote said. Okay, so we've established the rule book. We know what forces are. But how do these forces actually interact out in the real world? Like, how do we arrive at that perfectly peaceful, quiet wrestling match we talked about at the very beginning of the show?
Okay.
This brings us to a concept called equilibrium.
Equilibrium is essentially the holy grail for a structural engineer.
I was looking through the specific case studies in our notes, and there's this classic engineering problem that paints the picture perfectly. Imagine a car. Let's say it's a sleek, heavy Ford sedan.
Okay, heavy car.
And it is parked perfectly still on a steep hill. Let's say the road is angled at a 20-degree slope. The driver has walked away. The car isn't rolling backward down the hill, and it certainly isn't floating up into the sky. It is perfectly frozen in place.
That frozen state is equilibrium. In physics terms, it means the net force acting on the object is exactly zero.
Zero.
Yep. All those invisible wrestles we discussed are pushing and pulling against that car with the exact same amount of effort, resulting in an absolute stalemate.
But the car weighs like thousands of pounds. There's a massive amount of energy involved there.
There is an incredible amount of energy, but it is entirely balanced. For that specific car parked on that specific 20-degree slope, there is a core trinity of forces locked in combat to keep it stationary.
Okay, let's walk through this trinity because it really reveals the invisible architecture all around us. First up in the trinity, we have gravitational force, or, simply weight.
Right. This is our invisible field force at work. The Earth has an immense mass, and it is pulling the mass of that Ford sedan toward it.
But the direction of the vector is what's really interesting here, because the car is parked on a hill. You'd intuitively think gravity pulls, I don't know, down the hill. But gravity doesn't care about the angle of the street, does it?
Not at all. Gravity operates on a strict vertical axis. The vector for gravity points straight down toward the exact center of the Earth, regardless of what surface the car is resting on. It is the ultimate anchor.
Our notes actually dedicate a lot of space to just how massive a deal gravity is across completely different engineering disciplines. It really is the ultimate anchor. Like, if you look at civil engineering, they're basically fighting this massive defensive war against gravity.
Oh, awesome.
Think about a massive city skyline, just skyscraper after skyscraper. Those buildings weigh hundreds of thousands of tons. Civil engineers have to design these deep, complex foundation systems just to handle those immense downward forces.
Right, because without those foundations, a skyscraper would simply sink into the soil or tilt under its own massive load.
Just disappear into the dirt.
Exactly. The engineers are literally building giant subterranean hands of concrete and steel to push back upward against the Earth's gravitational pull.
Okay.
They are demanding equilibrium.
But then you look at aerospace engineering, and they have an entirely different relationship with gravity. They aren't trying to just sit safely on the ground. They are actively, violently trying to escape it. I was reading the notes about the STS-1, that's the maiden flight of the space shuttle, back on April 12, 1981.
A truly monumental day in engineering history.
The numbers are staggering. To get that shuttle off the ground, aerospace engineers had to calculate exact escape velocities. They had to harness millions of pounds of explosive thrust just to overcome that invisible downward vector.
To punch through the field force.
Exactly, just to achieve a stable orbital trajectory. It's the exact same fundamental force, gravity. But the civil engineer is trying to peacefully distribute it into the ground, while the aerospace engineer is basically trying to punch it in the face.
It is a brilliant contrast.
Sure.
But let's return to our Ford sedan parked on the hill.
Right, back to the hill.
Gravity is relentlessly pulling it straight down toward the center of the Earth. So why doesn't the car just phase straight through the asphalt and fall into the dirt?
Because the road is solid. Which brings us to the second force in our equilibrium trinity, the normal force. Now, I have to stop here and complain for a second.
Oh no, what's wrong?
Why do physicists call it normal? Honestly, out of all the incredible dynamic forces in the universe, normal force sounds so incredibly boring.
I know.
When I first read it, my brain just automatically translated it to the regular, everyday, nothing special force.
You are definitely not the only one to complain about that. It is a terrible public relations problem for a really vital mathematical concept. In physics and mathematics, the word normal does not mean ordinary or mundane.
Good to know.
It actually has a very strict geometric definition. Normal means perpendicular.
Ah, perpendicular, meaning it intersects at a 90-degree angle.
Precisely. The normal force is the force exerted by a surface pushing back against an object that is pressing into it. And it always acts exactly perpendicular to that surface.
Okay, let's map that back to the car on the hill. The road is slanted at a 20-degree angle. Gravity is pulling straight down to the center of the Earth. But the normal force isn't pushing straight up into the sky.
Right.
It's pushing away from the slanted road at a 90-degree angle.
Yes. It is the solid molecular structure of the asphalt physically fighting back against the tires, preventing the mass of the car from falling through the road. It's basically the floor saying, "You shall not pass."
See, you shall not pass is a much better name than normal force.
I'll write to the physics board.
Please do. And this force is incredibly dynamic, too. Our research shows that the normal force acts as both a support system and a primary driver of motion. Let's talk about the support side first, specifically in civil and automotive engineering.
Okay, yeah. This is where the normal force dictates your safety literally every time you get in a car. The upward normal force of the road pushing against your tires is actually what determines your grip.
Because if the road didn't push back, you'd just be floating. Right.
Exactly.
And the notes mention this interaction is what ensures the necessary friction coefficient is maintained for safe driving. So basically, without that perfectly calculated perpendicular pushback from the ground, your brakes wouldn't even work. You'd just skied infinitely.
Yeah, the grip of your tire is directly proportional to how hard the normal force is squishing the rubber into the pavement. This is why a heavier car can sometimes take longer to stop. The weight increases the normal force, but the momentum it carries often outpaces the friction those tires can realistically provide.
That makes total sense. But the example that really blew my mind was in mechanical machine design. The normal force isn't just about floors holding things up. It's about how every machine on Earth actually moves.
Oh, gears.
Yes. Think about the transmission in your car. It's full of interlocking metal gears.
This is where normal, meaning perpendicular, becomes the absolute star of the show. When two gear teeth interlock and press against each other, the face of the driving gear pushes against the face of the receiving gear.
And because they are angled teeth, that push is a normal force. It's acting perpendicular to the tiny microscopic surface of the metal tooth.
Yes, and that normal force between the interlocking gear teeth converts the raw driving energy into a tangential force, and that tangential force produces torque.
Torque, the rotational twisting force.
That's the one.
So literally, the engine of your car spinning the wheels is completely dependent on engineers calculating the exact normal force between tiny metal teeth inside the gearbox. Like if they get the angle of the gear tooth wrong, the normal force points the wrong way, the torque disappears, and the gears probably just shatter into a million pieces.
It is the invisible driver of the Industrial Revolution.
Wow.
But pulling back to our Ford sedan, parked on the 20-degree slope.
Right, our poor abandoned car.
We have gravity pulling it straight down. We have the normal force of the road pushing back up at an angle to keep it from falling through the earth. But the car is on a hill.
Yeah.
Why isn't gravity just pulling it backward down the slope?
That brings us to our third invisible wrestler, frictional force.
The savior.
Exactly. Gravity wants to pull the car down the 20-degree incline. The normal force is just holding it up from falling through. But friction is the vector acting perfectly parallel to the slope, pointing up the hill. It is directly opposing the downward motion and keeping the vehicle entirely stationary.
Friction is fascinating because, in popular culture, friction gets a really bad reputation.
Oh, for sure. We think of it as a nuisance. It causes wear and tear on our shoes, it causes engines to overheat, it slows things down.
But to an engineer, friction is the ultimate controller. Without it, the whole world is basically an ice rink.
Our source material calls it exactly that, the controller. And it uses two incredibly intense automotive engineering examples to show how engineers basically weaponize friction for our safety and convenience. Let's look at braking systems first.
The physics of a modern disc brake system is just a masterclass in managing energy.
So imagine looking through the spokes of your car tire. You'll see the shiny metal disc, that's the rotor, and a metal clamp grabbing it, which is called the caliper. Now you're flying down the highway at 70 miles an hour. Your car has an unbelievable amount of forward kinetic energy. You need to stop because there's traffic ahead. You hit the pedal.
Right.
But you can't just magically delete all that kinetic energy from the universe, right?
No, the first law of thermodynamics expressly forbids it. Energy cannot be created or destroyed. It can only change forms.
So the engineers designed a system to forcefully crush two materials together. When you hit the pedal, hydraulic pressure forces the brake pads against that spinning metal rotor. The resulting friction violently grabs the rotor, and it literally converts the vehicle's forward kinetic energy into raw heat.
And not just a little heat either.
No.
Brake rotors can reach hundreds of degrees during a hard stop. They can literally glow red hot.
That's terrifying.
It is. So the engineering challenge isn't just creating the friction, it's dissipating that immense heat into the air quickly enough so the metal doesn't melt and your brakes don't completely fail.
It's literally an energy transformation machine. You are turning speed into fire, essentially, just so you can stop at a red light.
Exactly.
But friction isn't just for stopping things, it's also for starting them.
Think about a manual transmission car.
The clutch system. Right, you have an engine that is running and spinning thousands of times a minute, and you have a heavy car with wheels that are currently perfectly still. If you just took a solid metal rod and jammed the spinning engine directly into the stationary wheels, what would happen?
The shock would be catastrophic.
Yeah.
The car would violently stall, or more likely you would physically snap the metal axles in half. The difference in energy states is just way too aggressive.
So engineers use friction as a mediator. The clutch system uses a series of discs, the flywheel, the clutch disc, and the pressure plate. As you let your foot off the clutch pedal, these plates slowly press together.
And, crucially, they are allowed to slip against each other initially. That controlled friction transfers the spinning power from the engine to the transmission really smoothly. It gradually matches the speeds of the two systems until they lock together fully without slipping.
It's like a beautifully choreographed dance of physical forces, slipping just enough at the beginning, absorbing the shock, and then grabbing tight so all the power flows through to the wheels.
It's brilliant.
Okay, so we've covered the basics. We know how to push, how to pull, how to rest in perfect equilibrium, how to stop, and how to start. But here is where our deep dive takes a really serious turn. The physical world isn't just, solid blocks sliding on-ramps. What happens when engineering requires materials to stretch across the open sky? Or to bend violently without snapping? Or to spin at dizzying, nauseating speeds?
Yeah, we have to leave rigid bodies behind and enter the realm of dynamic material forces. This is where engineering really becomes an art form.
Let's start with stretching, the force of tension. This is all about suspending massive loads, and the most breathtaking visual of tension is a cable-stayed bridge.
Oh, they are gorgeous structures.
Imagine driving toward a major city over a massive river, and you see these giant concrete towers reaching into the clouds with dozens of thick steel cables fanning out down to the roadway.
A cable-stayed bridge is an absolute masterpiece of tension engineering. Like in an older traditional bridge, you might build a dozen thick concrete pillars planted right in the riverbed, pushing straight up from underneath to support the road.
That's the normal force again.
Exactly. But building pillars in deep, fast-moving water is incredibly dangerous and insanely expensive. So instead, engineers use tension. They build one or two massive towers on solid ground or shallow water. Then they basically hang the road deck from those towers using cables.
So the cables are pulling the road up?
Yes. The entire weight of the cars, the concrete, the asphalt, it all pulls downward due to gravity. That downward force aggressively stretches the cables. The cables are under immense tension, but steel possesses this fascinating material property. It is exceptionally strong under tension. You could pull a steel cable incredibly hard before its molecular structure yields and snaps.
So the cables take all that heavy downward force from the cars, stretch super tight, and pass that force up to the top of the tower, which then compresses down into a single massive foundation.
Right, it routes the invisible forces completely around the empty space above the water.
It's brilliant. But tension isn't just for massive, glamorous bridges, is it? The research points out a much more common example: overhead power lines.
Oh yeah, everywhere you look.
You look up at twilight and see these wooden utility poles with thick black wires draped between them against the sky. Honestly, I've never looked at a power line and thought about physics. I just think, man, I hope the power doesn't go out in the storm.
But those lines are constantly under dynamic tension, and managing it is actually one of the biggest headaches for electrical engineers.
Because they can't just pull the wire as tight as possible between the poles, right? Like a guitar string.
No, absolutely not, because the environment is constantly attacking them. The wires are made of metal, usually aluminum and steel, and metal undergoes thermal expansion and contraction. So on a blistering hot summer day, the metal physically expands. The wire gets longer.
And when it gets longer, it sags down toward the street.
Exactly. And if an engineer didn't calculate the tension correctly, the line sags too low, hits a passing semi-truck, and an entire neighborhood loses power. Or it hits a dry tree and starts a wildfire.
But then winter comes.
Right. On a freezing winter night, the metal contracts. It shrinks and pulls tighter between the poles. The tension skyrockets. Now, add the weight of a severe ice storm, where an inch of solid ice coats the entire wire. The downward gravitational pull increases massively, and the wire is already pulled tight from the cold.
Wow.
If the starting tension was too high, the line will literally snap under the strain. Engineers must constantly calculate and monitor these tension tolerances to ensure safe power transmission through all weather extremes.
They are literally balancing the slack and the stretch on a tightrope. It's wild. Okay, so that is stretching. Let's talk about flexing, the elastic force. And I have to admit, when I was reading this section, I had a very visceral, anxious reaction.
Oh, I know what you're going to say.
Because the primary example they use is an aircraft wing.
It unnerves a lot of people.
Anyone who has ever flown on a commercial jet knows this exact feeling. You're cruising at 30,000 feet, you hit a patch of rough turbulence, the plane drops, your stomach jumps right into your throat. You look out the little oval window and you see this massive, heavy metal wing bending violently up and down.
Flapping almost.
Flapping, bending. My brain immediately screams, metal is supposed to be rigid. If it bends, it's going to snap off and we are all going to fall out of the sky. Why on earth do aeronautical engineers design wings to do that on purpose?
Because it is entirely counterintuitive to how we experience solid metal in our daily lives.
Yeah.
We associate rigidity with strength. But in dynamic environments, rigidity is actually the enemy of durability.
Wait, really? How does being bendy make it stronger?
Well, think about an old, dry twig. It's incredibly rigid, but if you push on it, it instantly snaps.
Right.
Now think of a fresh, green willow branch. It bends and flexes, but it is almost impossible to break it in half. Aircraft engineers apply this exact principle. If an airplane wing were perfectly immovably stiff, what would happen during turbulence?
I don't know, you'd feel the bumps.
Every single violent jolt of air pushing up on the wing would transfer that energy directly into the fuselage, the body of the plane where you are sitting.
Oh, so the ride would be unimaginably rough.
Horrifically rough. You'd be bouncing off the ceiling. But worse than that, the point where the rigid wing attaches to the body of the plane would experience catastrophic stress. The metal at that joint would suffer from rapid metal fatigue, microscopic cracks would form, and eventually the wing would snap off.
So the bending is actually a survival mechanism.
Yes. The slide specifically notes that wings are intentionally designed to flex elastically. By allowing the wing to bend, the structure acts as a giant aerodynamic shock absorber. It absorbs the sudden upward force of the turbulent air and distributes it slowly across the entire length of the wing.
That makes so much sense.
It reduces overall drag, softens the ride for the passengers, and crucially, prevents catastrophic structural failure.
So the fact that the wing is flapping a little bit is exactly why I am safe. I will try to remember that next time I'm white-knuckling the armrests.
Good luck.
But that concept of a shock absorber translates directly down to the ground too. Automotive suspension.
Yes, mechanical engineering applies elastic forces constantly to manage unpredictable environments on the road.
We've all driven over a massive pothole. If your car didn't have a suspension system, your spine would just shatter. The engineering notes break the suspension down into two parts. First, you have the coil springs.
Right.
The spring absorbs the sudden kinetic energy from the road irregularity through elastic deformation. Essentially, the tire hits the bump, the wheel is shoved violently upward, but instead of shoving the whole car up, the spring simply compresses. It temporarily stores that violent energy.
But a spring alone is a disaster. If you just had springs on your car, what happens after you hit the bump?
The spring uncoils and pushes the car back up, and then gravity pulls it down and the spring compresses again. You'd just be bouncing down the highway like a pogo stick. Boing, boing, boing for miles.
Exactly. And while that's nauseating for the passenger, it's actually deadly for the driver. Because when the car bounces upward, the tire lifts off the road. When the tire lifts off the road, your normal force drops to zero.
And if the normal force drops to zero, as we learned earlier, friction drops to zero. You have no grip, you can't steer, and you can't brake.
Precisely. That is why engineers pair the elastic spring with a damper, which is commonly known as a shock absorber. The damper uses hydraulic fluid to resist the bouncing motion. It dissipates the stored energy from the spring as heat. It allows the spring to compress once, and then smoothly and strictly returns it to its resting state without bouncing.
Which maintains that crucial tire contact with the road.
Yes.
It all connects perfectly back to our equilibrium trinity. We need the normal force to survive. Okay, so we've stretched the bridge cables, we've flexed the airplane wings, now we spin. The centripetal force. Our source material calls this the circular director.
Moving an object in a straight line is easy. Moving an object in a circle requires constant aggressive intervention.
Why is that?
Newton's first law tells us that an object in motion wants to stay in a straight line. If you're swinging a rock on a string around your head, the rock desperately wants to fly away in a straight line. The string provides a constant inward pulling force, the centripetal force forcing the rock to turn at every single microsecond.
And engineers use this circular force in some pretty brilliant ways. Let's look at the microscale first. Medical and manufacturing centrifuges. Imagine a high-speed laboratory machine holding a bunch of test tubes. It spins them around at thousands of revolutions per minute.
This is a really vital diagnostic tool. When you go to the doctor and get your blood drawn, your blood is a mixture of red blood cells, white blood cells, and a watery fluid called plasma. If a doctor needs to test just your plasma, they need a way to separate the liquid from the cells.
And you can't exactly pick them apart with tweezers.
No, you definitely can't. But the cells are denser and heavier than the plasma. So they put the blood in a test tube and spin it in a centrifuge. Because the test tube is spinning so fast, the denser, heavier components have a higher inertia. They want to fly off in a straight line with more force.
Oh, I see.
The bottom of the test tube pushes inward on them, providing the centripetal force. This effectively creates an immense artificial gravitational field at the bottom of the tube.
The notes phrase it perfectly. The force of the spin weaponizes density. The heavy red blood cells are shoved violently to the very bottom of the tube, and the lighter plasma rests perfectly clear on top. You separate fluids using nothing but a circle and speed.
It is incredibly efficient.
But then our research zooms way, way out, from a tiny vial of blood to the total vacuum of space.
Yeah.
Aerospace engineering. We're talking about artificial gravity.
Oh, this is great. If you are a fan of science fiction movies, you definitely know the visual. A massive, glowing space station shaped like a giant ring, rotating slowly against the stars.
It looks so cinematic, but it is deeply grounded in actual physics. We know that long-term exposure to microgravity in space is devastating to the human body.
It really is.
Astronauts lose massive amounts of bone density and muscle mass because they aren't fighting gravity every day. Their bodies literally just start to waste away.
So, if we ever want to travel to Mars or live in deep space, engineers have to fake gravity, and they do it using centripetal force.
Okay, walk me through how spinning a ring makes you feel heavy, because that's wild.
Think about being in a car that takes a really sharp turn to the left. What happens to your body?
I get shoved hard into the passenger side door.
Exactly. Your body wants to keep going straight, but the car is turning left. The door pushes against your shoulder to force you into the turn. Now imagine a space station shaped like a giant wheel. The astronauts live on the inside of the outer rim. The station starts to spin.
Okay.
The astronauts' bodies want to float away in a straight line into space, but the floor of the space station is constantly curving up into their path.
So the floor is effectively the passenger side door in the car turn.
Yes, the floor pushes against their feet, providing the inward centripetal force necessary to keep them moving in a circle. And to the astronaut, That constant push against the bottom of their feet feels absolutely identical to the normal force of standing on Earth.
They are being shoved outward into the floor by their own inertia. It completely successfully mimics natural gravity. It's just mind-blowing.
It really is.
Now, we've spent this entire time talking about highly visible physical mechanical movements, pushing blocks, spinning test tubes, bending wings. But section 4 of our deep dive takes us into an entirely different realm, the most dominant force in modern human society, and it is entirely, utterly invisible.
The electromagnetic force.
The
Invisible ways.
Our notes subtitled this section Communication and Healing, which is a really poetic way to frame electromagnetism. Let's start with communication. Telecommunications and signal transmission. I hold a smartphone in my hand every single day.
We all do.
Right. I stream music, I send videos, I look at maps, but I rarely, if ever, stop to think about the absolute wizardry happening in the air around my head to make that possible.
We take it completely for granted, but the air around you is thick with an invisible architecture of oscillating fields.
How does an engineer send a photograph through empty space without wires? Like, fundamentally.
By manipulating the electromagnetic field. Electric field and magnetic fields are fundamentally linked. When an electric charge moves, it creates a magnetic field. When a magnetic field fluctuates, it creates an electric field.
They trigger each other.
Exactly. They dance together, oscillating back and forth. This oscillation creates an electromagnetic wave that propagates out into space at the speed of light.
And the numbers our research drops here are staggering. Engineers generate and modulate these waves across a massive spectrum, ranging from 3 kilohertz all the way up to 300 gigahertz.
That frequency range determines everything about how we communicate. Low-frequency radio waves can travel for hundreds of miles and penetrate thick concrete walls. That's why you can listen to FM radio down in your basement.
Oh, right.
High-frequency waves, like microwaves or millimeter waves used in 5G cellular networks, they carry a massive amount of data very quickly, but they get blocked by trees and buildings easily.
But how does the wave actually carry my text message? It's just energy, right?
This is where the engineering genius comes in. Modulation. They don't just blast a continuous, unchanging wave. They take that wave and they slightly, rapidly alter its properties.
Like how?
They might slightly compress the frequency or change the height of the amplitude. They encode the digital ones and zeros of your text message into the physical shape of the invisible wave.
So my phone is essentially yelling a highly complex Morse code pattern in invisible light, which ripples across miles of open air, hits a metal antenna on a cell tower, and gets decoded back into a digital photo instantly. It is literal magic made real by math. But electromagnetism isn't just for sending memes, obviously. The research shifts to biomedical engineering, specifically one of the greatest engineering achievements of the 20th century.
The MRI, magnetic resonance imaging.
Now, I've had an MRI on my knee. From the patient's perspective, it just looks like a giant, very loud plastic donut that they slide you into. But the mechanics happening inside that machine are deeply, wonderfully strange.
It relies on the magnetic properties of your own body at an atomic level.
Okay, I want to try an analogy here to see if I truly grasp how this works, because the physics are really dense here. Our bodies are made mostly of water, right?
Right.
Which means we are absolutely packed full of hydrogen atoms.
Billions and billions of them.
And normally the magnetic moments, the tiny magnetic fields of those hydrogen atoms, are just pointing in totally random directions.
Yep.
Pointing up, down, sideways, total chaos.
Correct. They are completely unaligned.
So when they slide you into the MRI tube, they turn on a massive superconducting magnet, a static magnetic field that is thousands of times stronger than the magnetic field of the Earth itself. It is so strong, it can literally rip a wrench out of someone's hand from across the room.
It's incredibly powerful.
I like to think of this step like an orchestra warming up. All the musicians, the hydrogen atoms, are playing random notes looking in different directions. Complete chaos. But then the static magnetic field turns on, the conductor steps up to the podium, and suddenly, every single musician stops what they are doing, turns perfectly straight, and faces the conductor. All the hydrogen atoms snap into total alignment.
That is a remarkably precise way to visualize the static field alignment. The sheer force of the magnet physically forces the atomic nuclei into a uniform state.
Okay, but just having the atoms lined up doesn't take a picture of my torn knee ligament. How do we get the actual image?
This is where we introduce a second electromagnetic force, the radio frequency pulse.
Going back to our symphony analogy, the musicians are all at attention. The radio frequency pulse is like the conductor pointing his baton directly at the brass section and yelling, "Play one loud note."
Yes. The MRI machine fires a very specific, perfectly tuned pulse of radio waves right into your body. Because the hydrogen atoms are under that immense magnetic tension, they absorb the energy of that radio pulse. They get excited. They vibrate out of alignment.
They play their loud note.
Exactly. But the pulse only lasts a fraction of a second. When the radio pulse turns off, the hydrogen atoms relax back into their aligned state. And as they relax, they release that stored energy. They basically echo the radio wave back out of your body.
And the MRI machine isn't just a magnet, it's a giant, incredibly sensitive antenna listening for that echo.
It listens to the atomic echo. And here is the true genius part. Different types of tissues in your body have different concentrations of water.
Oh, okay.
Fat has a different amount of water than muscle. Muscle is different from a tumor. Bone is different from blood.
So because they have different amounts of water, they release that radio echo at slightly different speeds and intensities.
Precisely. The computers map the timing and intensity of every single echo coming out of your body and translate that data into a stunningly high-resolution, high-contrast visual image of your soft tissues. You are literally hearing the quantum mechanical makeup of a human body and turning it into a map, all without making a single surgical cut.
A symphony of invisible waves acting as the ultimate diagnostic tool, which ties directly back to that amana we discussed at the top of the show, the sacred trust of using forces to protect and preserve human life.
It's the perfect example of it.
But as incredible as an MRI is, as mind-bending as cell phones and space stations are, our deep dive takes a massive, abrupt pivot right here in Section 5.
The great humbling.
The great humbling, indeed. Up until this point, our research has basically been a victory lap for human ingenuity. It's been all about our math, our calculators, our massive supermagnets and antennas. But suddenly, the documents basically say, hey, humanity, take a seat. You are actually incredibly late to the engineering party.
It introduces the ultimate perspective shift, learning from the original blueprints.
And it brings back the philosophical framing, too. It quotes Surah An-Nahl, chapter 16, verse 79. Do they not see the birds controlled in the sky? None holds them up except Allah. Indeed, in that are signs for a people who believe.
It introduces the scientific discipline of biomimicry.
Biomimicry.
Yeah. By observing the natural world carefully, engineers discover that aerodynamics, material science, and energy efficiency have already been absolutely perfected.
Not just prototyped, right. Perfected through millions of years of natural selection.
Exactly. The core insight here is that true innovation requires humility. A great engineer must admit that nature's research and development department has been running for eons, longer than human civilization. Sometimes, the smartest, most efficient way to solve a modern engineering challenge is simply to walk outside, find an animal or a plant that solved the exact same problem a million years ago, and humbly copy their homework.
The case studies in our research on this are completely wild. Let's look at aerodynamics first. Stealth and speed. We have the B-2 stealth bomber.
Classic.
It is a legendary piece of aerospace engineering. It looks like a sleek, black flying wing. It's a multi-billion-dollar aircraft. But its shape didn't come from a computer simulation, did it?
No, the shape was heavily inspired by the peregrine falcon.
A bird.
Yes, specifically during its hunting dive. A peregrine falcon can dive at speeds over 200 miles per hour to strike its prey.
The physical forces on a bird moving that fast must be insane.
They are. But it's not just about surviving the speed. Think about the falcon's objective. It needs to dive bomb its prey, but it needs to do it silently. If a small animal hears a massive rush of displaced air screaming down from the sky, it's going to run away. So the falcon has evolved a specific swept wing posture and lacks a traditional protruding tail during its dive. This allows it to slice through the air without leaving a massive pressure wave.
It doesn't disturb the air behind it, and aerospace engineers looked at that silent, undisturbed air and realized that was the secret to radar evasion.
Exactly. Radar detects objects by bouncing radio waves off of hard surfaces and turbulent wakes. By mimicking the swept shape and the tailless design of the Falcon, the B-2 bomber cuts through the sky with an incredibly small radar signature. The military wanted stealth, and the Falcon had already perfected it.
That's a beautiful translation from biology to modern machinery. But the second aerodynamic example in the notes was the one that really stumped me at first. The Shinkansen, the Japanese bullet train.
One of the modern marvels of public transit.
The notes pair the bullet train with a tiny, brightly colored bird called the kingfisher. Now, I understand a bird inspiring a plane, they both fly in the air, but a bird inspiring a train, a heavy metal tube driving on the ground, how does that connect?
It connects through the intense, highly problematic physics of fluid dynamics. When the early high-speed bullet trains were built in Japan, they were incredibly fast. They operated out in the open air perfectly fine. But Japan has a very mountainous terrain, which means the train tracks go through hundreds of long tunnels.
And a tunnel is basically just a confined concrete tube.
Right. So imagine a train with a flat, blunt nose entering a tunnel at 150 miles per hour. The train violently compresses the air trapped in the tunnel in front of it. It acts exactly like a piston shoving air down a cylinder.
Because the air can't get out of the way fast enough.
Exactly. So the train pushes this massive, dense wall of pressurized air all the way through the tunnel. And when that wall of high-pressure air finally burst out the exit of the tunnel,
Ooh.
a literal sonic boom
Okay.
was a massive problem. The micropressure waves were so loud, they were terrifying residents living near the tunnel exits, waking people up in the middle of the night, and even threatening structural damage to the tunnels themselves.
Oh, wow.
The engineers were completely stumped on how to solve it without significantly slowing the trains down, which completely defeats the purpose of a bullet train.
And the answer was a bird that eats fish.
The lead engineer on the project was an avid bird watcher. He was studying the kingfisher. The kingfisher hunts by diving out of the air and into the water to catch fish. Now, air is a low-resistance fluid. Water is a highly dense, high-resistance fluid.
So diving into the water is exactly like the train diving into the dense air of the tunnel. It's a fluid boundary problem.
Precisely. If a regular bird dives into the water, it makes a massive splash. It displaces a lot of water violently, which scares the fish away and could actually injure the bird. But the kingfisher has a very long, specialized wedge-shaped beak. It slices through the boundary between air and water flawlessly, barely leaving a ripple. It glides in without a splash.
So the engineers went back to the drawing board and completely redesigned the front of the bullet train. They gave it a massive 50-foot-long nose that looks exactly like a kingfisher's beak.
And the results were revolutionary. Mimicking that splashless dive completely eliminated the sonic booms. The train sliced through the air in the tunnel instead of pushing it. But it had incredible side effects, too.
Like what?
Because it was no longer fighting massive air resistance, the train's top speed actually increased to 186 miles per hour, and its electrical efficiency improved drastically. They saved massive amounts of power just by copying a bird's beak.
By humbling themselves, they revolutionized rail transport. It's so cool. Okay, we've talked about air and trains. Let's talk about water and fluid efficiency. The research highlights microscopic shark skin.
The texture of survival.
The notes show a microscopic close-up of a shark's skin. We normally think of an apex predator swimming fast as being perfectly sleek and smooth, right? Like if you want a race car to go fast, you polish and wax it until it shines. But under a microscope, a shark's skin is made of tiny, jagged, overlapping scales called riblets. It looks like rough sandpaper. Why would an animal that needs to swim fast be covered in sandpaper?
Because smoothness is an illusion when you are dealing with fluid dynamics. If a perfectly smooth surface moves quickly through water, the water drags against the surface. This creates microscopic eddies, tiny, chaotic whirlpools of turbulence right next to the skin. Those little turbulent whirlpools grab the object and pull backward, creating massive drag.
So being perfectly smooth actually slows you down.
It does. But the microtextures of a shark's skin, those jagged riblets, deliberately channel the water. They manage those tiny turbulent vortices, organizing the flow and effectively creating a microscopic boundary layer of water that acts like a lubricant. The shark slides through the ocean with almost zero friction.
And humans definitely stole this idea. The research notes that this exact biological principle was applied to competitive swimsuits. I remember this happening at the Olympics. They designed swimsuits with microscopic shark-scale riblets, and the swimmers were breaking world records left and right.
Yes, I remember that too.
The suits were so hydrodynamically efficient that the international swimming governing bodies actually banned them. They considered it technological doping.
It is the ultimate proof that nature's engineering is vastly superior to ours. We also apply that exact shark skin texture to the exterior coating of massive cargo ships to reduce drag and save millions of gallons of diesel fuel.
That's incredible. So biomimicry changes how we move, but it also changes the very materials we use. The final section of our research dives into masterclasses in material science.
Chemistry perfected by evolution.
The first example here is the Lotus effect, superhydrophobicity.
A fantastic word. Superhydrophobic means extremely violently water repellent.
Right. Imagine a lotus plant. It
Mm.
grows in swamps. It grows in muddy, dirty, stagnant water.
Yeah.
Yet if you look at a lotus flower or its massive green leaves, they are always immaculately clean, not a single speck of dirt. How does a plant living in literal mud stay pristine?
The secret lies in the microscopic architecture of the leaf's surface.
The notes explain that if you zoom in, the lotus leaf is covered in tiny microscopic pillars, and those pillars are coated in special wax crystals.
Right, and because of these structures, water cannot lay flat against the leaf. The contact angle is extremely high. So when a raindrop hits the leaf, it doesn't spread out and get the leaf wet. Instead, the water is forced to remain in a perfect, rigid sphere.
Like a glass marble.
Exactly. And because it's a perfect sphere resting on tiny pillars, it has almost no friction. The slightest breeze or tilt of the leaf causes the water droplet to roll freely across the surface. And as that spherical droplet rolls, it acts like a sticky snowball.
A sticky snowball.
Yeah, it picks up every single microscopic particle of dust, mud, and debris on the leaf and carries it away. The water literally cleans the plant.
And engineers saw this biological self-cleaning mechanism and just immediately commercialized it. The research points out that the lotus effect is now used to engineer self-cleaning glass and exterior building textiles. Imagine a skyscraper covered in thousands of windows in a highly polluted city. You don't need to hire people to hang off the side of the building with squeegees anymore.
That's the goal.
The glass is manufactured with biomimetic nanostructures, and every time it rains, the water just rolls off, taking all the smog and dirt with it.
It reduces maintenance costs, saves water, and entirely eliminates harsh chemical cleaners. All because someone studied a swamp flower.
But the final material science example in our research is the one that really gives me pause. It represents the absolute pinnacle of what we are trying to achieve. Spider silk.
The holy grail of material engineering.
The text states boldly that spider silk possesses an unmatched strength-to-weight ratio. Ounce for ounce, it is stronger than structural steel and significantly tougher than Kevlar, the material we use in bulletproof vests. Yet it is incredibly flexible, lightweight, and elastic. It can stretch up to 5 times its relaxed length without breaking.
If human beings could manufacture a synthetic fiber with the exact mechanical properties of spider silk, it would revolutionize almost every industry on Earth.
Really, every industry.
Oh, absolutely. We could build suspension bridges with cables as thin as a pencil. We could create bulletproof clothing that feels like light summer silk. We could make artificial ligaments for surgical joint replacements that would literally never wear out.
But here is the insight that really hits home for me from the notes. Look at how humans currently make strong materials like steel. It is a violently abusive process. We have to rip massive craters in the earth to mine iron ore. We have to transport it across the globe. We build massive, intensely hot blast furnaces, burning thousands of tons of coal and fossil fuels, spewing smoke and carbon into the atmosphere just to heat metal to 3,000 degrees so we can pour it.
That's awful.
It's an incredibly energy-intensive, highly polluting process.
A brute force approach to engineering.
Exactly, brute force. And yet, right outside my window right now, a tiny, harmless spider is manufacturing a material that is technically superior to our best steel. And the spider is doing it at room temperature, quietly, using a little bit of water and the protein from a fly it ate yesterday.
That is the ultimate humility. Nature achieves superior results with a fraction of the energy and zero toxic byproducts.
Engineers are actively trying to map the molecular process of spider silk synthesis, aren't they? If we can unlock how to manufacture high-tensile materials at room temperature using natural proteins, we could drastically reduce the energy footprint of global manufacturing.
We really could. And that profound realization that we still have so much to learn about efficiency and sustainability from the natural world brings us to the perfect conclusion of our deep dive today. The final section of our research is titled The Ethical Engineer.
It ties everything back together. It brings us completely full circle to where we started our conversation today, the Islamic concepts of Amana, the Sacred Trust, and Khalifa stewardship.
The research summarizes the journey of an engineer into 3 core pillars. First, mastery requires understanding. You cannot build a safe world on guesses. Calculating those invisible forces, gravity, friction, tension, electromagnetic fields, is the absolute non-negotiable foundation. You have to do the rigorous math.
Because if you don't do the math, the bridge falls down and the sacred trust is broken.
Exactly. Second, innovation requires humility. Biomimicry proves that human beings do not have a monopoly on good ideas. The most advanced, elegant, and efficient solutions often come from quietly observing the perfect harmony of nature. We must be willing to learn from the kingfisher and the lotus.
And finally, the third pillar. Engineering is Amana. The research lays out a mandate for anyone studying this field. It says, your future calculations carry the weight of lives. Use this knowledge ethically, champion sustainability, and serve society as a responsible Khalifa of the Earth.
It is a beautiful synthesis of science and morality. It explicitly states that understanding the physics of a skyscraper's foundation is only half of your job. Building that skyscraper in a way that serves the community safely without needlessly polluting the air or destroying the environment around it, that is the true calling of an engineer. You are a steward of the physical forces, not just a conqueror of them.
There is a really powerful closing quote in the notes to wrap all this up. It says, mastering force is not just moving objects, it is honoring the balance.
Honoring the balance. It acknowledges all those invisible wrestlers. We spent the hour discussing the downward pulls, the perpendicular pushes, the violent friction, the magnetic alignments, and insists that we must interact with that invisible architecture with deep respect and ethical purpose.
It is such a refreshing, profound take on what is usually taught as a very dry, technical field. We started out today by asking you to look around your room and imagine the massive, invisible wrestling match happening all around you.
The perpetual stalemate of equilibrium.
Right. And over the last hour, we've unmasked the invisible architects enforcing that stalemate. We've looked at how aerospace engineers mathematically calculate how to break that stalemate to launch a shuttle into orbit. We've seen how automotive engineers use the violence of friction to enforce a stalemate and stop a speeding car.
We explored the dynamic world of bending wings and stretching bridge cables. We ventured into the invisible fields of electromagnetic waves that let us stream audio across the globe and map the water molecules inside the human body.
And then we got thoroughly humbled by a falcon, a bird that dives for fish, a swamp leaf, and a spider. We saw that the absolute pinnacle of human technological achievement is often just us slowly catching up to what nature has been doing flawlessly since the dawn of time.
It gives you a profound, lingering respect, not just for the equations and the math, but for the entire canvas we are doing the math upon.
Absolutely. So as we wrap up this deep dive into the forces of engineering, I want to leave you, the listener, with a final thought to mull over. We spent all this time talking about how humanity has built staggering monuments to our intelligence, skyscrapers that pierce the clouds, massive ships that cross the oceans, space stations that orbit the Earth, communications networks that span the globe. And we did it all by meticulously calculating, harnessing, and mastering these invisible forces.
But there's more to it.
There is. The next time you step outside, maybe tomorrow morning on your way to work, or even just looking out your window right now as this audio finishes, take a look at a simple bird gliding by, or a tiny bug crawling up the stem of a leaf, or a plant that manages to survive a brutal winter freeze. And ask yourself, what world-changing, entirely revolutionary blueprint of engineering is sitting perfectly quietly in your own backyard, just waiting for someone humble enough to finally notice it?